Okay, welcome everyone to the last lecture for this course in the summer school. Today we're going to leave behind constructions of IOPs. We spent 2 lectures discussing linear size IOPs for circuits and machines, primarily built using univariate polynomials. And today we'll talk a little bit about instead limitations of PCPs and IOPs, in some sense analogous to what we did towards the end of the interactive proof unit. In the case of interactive proofs, the limitations primarily came from interactive proofs where the prover sends a small amount of communication to the verifier, and we saw that sort of interactive proofs with small prover to verifier communication are not very powerful. Okay. The limitations of PCPs and IOPs more generally, they are much more, I would say, variegated, let's say. It really depends, which parameters you're trying to push for. So today we'll talk about a couple of the such limitations. Okay. So let's first talk about query complexity. So we almost proved the PCP theorem. Tom briefly talked about the PCP theorem by composition yesterday. Now, that was just PCP composition of components that we did not fully construct. Specifically, we omitted discussions of how you construct PCPs of proximity, robust PCPs. But nevertheless, at some point, basically, given the things that you could learn a little bit more to eventually be able to prove the PCP theorem, which gives you constant query complexity, polynomial proof length, and a sort of constant soundness error over a binary alphabet, right? And you could ask, look, how small can the query complexity be? Like, for example, could it be 1? Could it be 1 query? So let's just do like a quick proof that we do not expect to see interesting PCPs with query complexity exactly 1. Or I don't mean O of 1, I mean like literally 1. So suppose that some language has a PCP with some proof length over some alphabet, and it has query complexity 1. Okay. In this case, then we can actually construct a 1-round interactive proof for the language. How? Well, here's the prover for the interactive proof, and here's the verifier for the interactive proof. The verifier wants to check whether the PCP verifier outputs 1 or no. And of course, the PCP verifier wants to have access to the PCP string. We don't have a PCP string here. Or what we have is an IP prover. And look, there is just 1 query. We can just ask the prover to provide it. The honest prover will construct the PCP and provide the answer, right? And so first, the prover to verifier communication complexity is small. Like, we don't really pay for the whole proof length, we just pay for this single alphabet symbol, which is log sigma bits. Let me just go back to here. And we see that this simple construction works precisely because there's only 1 query, right? Because if we had had q equals 2, this would have been problematic, right? Because the answer of the prover to 1 query could have depended on what the other query is. But since there is only 1 query, whatever the prover answers, it can automatically define some underlying PCP, right? So somehow the fact that in a PCP, there is a string that is fixed, and then you sample the queries matters only when you have more than 1 query, right? If you have a single query, we might as well just ask somebody who gives me the answer. For any question that I would make, they have an answer to give me, the end, right? So are people convinced that this is a complete and sound transformation from a 1 query PCP to a 1-round IP? Right? And you might say, okay, so what? We've constructed a 1-round IP. Well, this is a 1-round IP where the prover sends a very small amount of information to the verifier, log sigma bits, right? So by the limitations on laconic, so laconic is the term, I forget if I used it or not, for interactive proofs where the prover sends a small amount of information. By the limitations that we have proved on interactive proofs that we saw in last week or Monday, we cannot expect log sigma to be, let's say, sublinear in the size of the problem or the size of the weakness for NP-hard languages. So if you remember, such a thing for 3SAT would, for example, contradict the exponential time hypothesis. Okay, so this is basically saying that unless you have a PCP where one symbol contains the full assignment of the 3SAT formula, in which case, of course, you can have a one-query PCP, you cannot have a one-query PCP for hard languages. Okay, so this is like a pretty simple kind of reduction to the laconic IP case, and then we rely on limitations of laconic IPs, right? Notice that it did require an argument, though. It required explaining, it seems intuitively that a one-query PCP should not be working for hard languages, but actually writing down why that's the case requires going first on interactive proof and then limitations on laconic interactive proofs. Any questions about this proof? This should basically tell you that to the extent that we can improve query complexity, we'll not be able to Q equals 1, right? Okay, so and you might say, okay, well, maybe special, Q equals 1 is special. What about Q equals 2? Okay, it turns out the situation for Q equals 2 is actually very, very different. And already, depending upon what parameters you want, when Q equals 2, you can start expecting something interesting. Any further questions about Q equals 1 before I move to Q equals 2? All right. So this brings to the question of two-query PCPs. Are there two-query PCPs? First, actually, curiously, the answer is no. In a very special case, if you have a binary alphabet and the PCP verifier is non-adaptive. If you remember, a non-adaptive PCP is one that makes all its queries in one batch, gets back the answers, and decides. It's not like it sends first a query, depending on the answer, it decides where to query the next one. In this special case of a binary alphabet, and the PCP verifier being non-adaptive, we cannot expect it. And it's actually for a very cute reason. So this is, I just wrote exactly what I meant, that if you have a PCP for some language that is perfect completeness, binary alphabet, and again, non-adaptive, then it must be decidable in P. And it's a very cute reduction. So we can view a candidate PCP string as just L variables. Let's call them Z1 through ZL. Okay, so these are variables that will take on the symbols for the candidate PCP string. And for every choice of randomness of the verifier, the decision of the verifier is some function on these variables, right? That depends on two variables among the L, right? Because on this randomness, I make these two queries. On this other randomness, I make these other two queries, right? So my decision is going to be some function of two out of the L variables, and this function depends on the randomness and on the input X, right? So therefore, if X is in L, there is an assignment to the variable such that the conjunction of all of these functions is 1. And if X is not in L, then there is no assignment that satisfies more than some epsilon S fraction of these functions, predicates, essentially, right? And deciding between these two cases is an instance of 2SAT, which is in P. Why is it an instance of 2SAT? Because whatever this function is, it depends on two variables. So you can just express it as like a clause on two variables, right? And here we have an end of clauses of two variables each, all right? And then 2SAT has this kind of this threshold phenomenon where 3SAT is NP complete, but 2SAT, there is even a linear time algorithm to solve it, right? And so in this extremely special case of binary alphabet and two queries and perfect completeness, it's just basically deciding whether there is a satisfying assignment or not is just an instance of 2SAT. And so here we cannot expect to encode any hard language into such parameters, okay? Hopefully that's clear, and you probably have seen the algorithm for 2SAT in some algorithms class. Usually it is sort of common to go through it. It's an example of a greedy algorithm. Right. On the flip side, if you allow to larger alphabets, so non-binary alphabets, we can achieve 2 queries. And so, for example, we can directly derive from the PCP theorem that every language in NP has a 2-query PCP over some large enough constant alphabet, maybe 0, 1 to the 1 million, okay? So where each symbol is some constant number of bits, just not 1 bit, all right? And how you do it is just this trivial query bundling that I think it was one of the worksheets, pretty sure. But essentially, you basically take the queries, you kind of wrap them up into larger symbols, you read a larger symbol, and you do a random consistency check, okay? And that's the 2 queries. So I don't want to go over it right now. It's not too important. And again, I believe it was in the worksheet, okay? You can always take some constant number of queries and kind of bundle them down to 2 queries, which is reading the queries in a bundle and a consistency check. It's a very good exercise if you haven't done it yet. But of course, when you do this bundling, right, necessarily you are going to have more than 1 bit in that bundle. That's why it requires an alphabet that is larger, okay? All right. Any questions about either of these cases, the case of 2-query PCPs?
I have a question.
Yeah.
So it seems that I don't see the difference with the adaptive case as well. Like it seems that the second query is defined by the first query and the randomness. No, like it reduces again to 2 SAT.
You mean here?
In yes. I mean,
it's not quite. So the second query may depend on the answer to the first query, not the randomness. So it could be that whether, let's say, z1 equals 0 or 1, the second variable in your kind of a 2-variable function might be this thing or some other thing, right? So I don't know how to write down a 2-SAT instance where the choice of variable that you depends on the answer to the first question.
Okay, I see. Thanks.
Yeah, good question. Any further questions here? Great. So these are like pretty simple points. This was just to kind of appreciate the extremal setting of 1 query and 2 queries. But so rather, as you can see here, however, when you moved to 2 queries, you took a hit in soundness error, right? So generally speaking, this leads to a question: if I allow myself to have a larger and larger alphabet, can I obtain a smaller soundness error? Because you are reading more information from the proof. Maybe this extra information should count for some better soundness. Okay, so this leads to like a fundamental question in PCP that is perhaps one of the hardest directions, which is, how do we simultaneously achieve small query complexity and small soundness error over a large enough alphabet? Okay. Now, notice here that the difficulty is that if you just take the PCP verifier and you run it multiple times, yes, you are reducing the soundness error exponentially, but you're also increasing the query complexity and randomness correspondingly, right? So just running the verifier multiple times is not like really like answering this question, right? So you want to look for ways to do that without increasing query complexity. And again, like even if you try to do randomness efficient error reduction rather than repeating the verifier on independent random strings, you kind of take them on a random walker on an expander. Still, yeah, you're using less randomness, but still you're making the same number of queries, like T times Q. So like a fundamental idea that is like really non-trivial is to bundle queries across multiple repetitions, okay? So you can think about, we're going to take the proof string over a quadratically larger alphabet with a quadratically proof length. So basically I write the proof string times itself, all possible combinations. So I have first symbol and first symbol, first symbol and second symbol, blah, 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 up to first symbol and last symbol. Then I start again, second symbol, first symbol, second symbol, second symbol, blah, 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 up to second symbol, last symbol. I write down all possible pairs of symbols, okay, of the proof. I have L squared of them, and then I bundle them up into like symbols that are twice the size as before, okay, over sigma squared. Now the idea is that we're going to run the verifier twice, but we're going to access things in bundles, so we are not paying for the extra queries. So it would look something like this. Let's say that I'm running the query algorithm on one randomness and the query algorithm on some other randomness. This is going to determine two pairs of indices for the two queries that I would run in one repetition and the other repetition. I break up these indices and I construct pairs of indices. So I put up I1 and J1 together, and I put J2 and I2 and J2 together. Here they are, right? These indices determine pairs, which I query, and I get back answers, and I deconstruct the answers and I provide them to the decision predicate, and I take the end of those. All right. So the proof length, and the alphabet size square in this case. All right. However, each query consists of one symbol per repetition, but we're still making two queries, right? So this is a concept that is called parallel repetition. Okay, it plays a very important role in the theory of probabilistic proofs. And of course, like there's a couple of observations here. First is that the soundness error definitely did not increase. We did not make the soundness error worse, because any one of these repetitions is kind of independent. So on their own, the adversary won't be able to fool us any more than it did in an iteration on their own, right? But the intuition is that the soundness error should be smaller, ideally roughly quadratically so, because we are running two independent repetitions, okay? Oopsie. The difficulty though, however, is that we don't know that the prover will write down a proof that has this form, okay? It might try to cheat to write like a proof that has inconsistencies about, like for example here, an honest proof will have pi1 through all of these and pi2 through all of these, right? And the same pi1 will appear here and here and also here, right? So it has all of these redundancies that an honest proof will have, but in general, a malicious proof may not, right? Now this subject of parallel repetition is a big one. We'll not much go over it. I'm just gonna tell you at high level that it exists. In general, this process leads to the T-wise parallel repetition of a given unadaptive PCP. You would expect T-wise parallel repetition to have this type of behavior where with a T-wise parallel repetition, your soundness error goes down exponentially in T. Of course, your alphabet will blow up in T and your proof length will blow up in T. The query complexity remains the same. But it turns out that the conjecture that the soundness error goes down as exponentially is false in general. There is a proof that the new proof length actually tends to zero as T leads to infinity. There's a very beautiful proof of it using Ramsey theory, okay? If you're interested in it, you can see, we're not gonna go over it today, but there is one of the recorded lectures from my fall 2020 course, will lead you through it, okay? It's a very, very clean application of a basic Ramsey theory result. And to this day, it's probably like the only way that we know to prove this goes to zero. And in a special case where you start out with two queries, we know that the soundness error kind of decays exponentially in T with some constant and some dependence on the alphabet. And this is a highly elaborate proof that uses information theory. Okay, this is called the parallel repetition theorem. First proved by Raz and then further improved by Thomas Hollenstein. So applied to the PCP theorem, this tells us that actually we can achieve any soundness error that we want with two queries, provided that we take a hit in the alphabet size and the proof length with that soundness error. Okay. There's a question by Vahid in the parallel repetition. Don't we need to make extra queries for consistency test? No. So this is kind of the magic of parallel repetition. It works as is. Okay. And somehow part of the reason is that there's so many redundancies that either if the prover has too many inconsistencies, then it will anyways make other things reject. Yeah, it's a complicated subject. It's not the main point of today. Yeah, there's no additional consistency checks. But the point is that with the parallel repetition theorem applied to the PCP theorem, you learn that you can drive down the soundness error to any constant that you want, provided you take a polynomial blow up in alphabet size and proof length, still with having two queries. Okay. The main limitation, however, is that proof length grows up with this dependency. And so if we want to keep polynomial proof length, which usually we do for things in NP, parallel repetition doesn't tell us anything for sub-constant soundness error. So if you want, for example, to say, I'm fine with a super constant alphabet size, why can't I expect a sub-constant soundness error? Okay, still with two queries. And as you will see in the other lecture later today, there are applications of PCPs, for example, to cryptography. And in those applications, actually, the regime that is most of interest is the fewest queries for the highest soundness error. And it's okay if you have a slightly large alphabet. Okay, in cryptography, that's a very good setting. So there is a big motivation to try to understand how do you go and leverage a large alphabet with a small soundness error without blowing up the proof length beyond polynomial. And parallel repetition won't get you there. Okay, and that's basically the main reason why I mentioned parallel repetition so far. All right, so this is like a big direction in PCP. In some sense, the last sort of wave of exciting PCP constructions that took place maybe in the last 10 years, they really focused on this regime. Okay, this is some of the most recent regime of PCP exploration that is closest to us today. So any questions about this particular slide? We're not spending more time on parallel repetition. It would require probably 1 or 2 lectures on its own. And if you want to look at this Ramsey theory application, you can see one of the recorded lectures from last fall. And if you want more information about this, then you actually have to read a paper. All right. So this leads to one of the kind of main open questions in the PCP sort of area. And the prevailing belief is that the soundness error epsilon is achievable with an alphabet size of poly 1 over epsilon and still with polynomial proof length. So this was actually conjectured a long while ago in a paper by Lare, Goldwasser, Lund, and Russell, 93, something that is known as the sliding scale conjecture that says that there is some constant queries, maybe not 2, maybe it's like 55, okay, such that for any error that is at least 1 over poly, you can simultaneously achieve polynomial proof length and soundness error epsilon that is potentially subconstant. And yes, you're going to take a hit in your alphabet size. All right. So this remains a conjecture. This regime is wonderful for cryptography. It in particular leads to asymptotically shorter succinct arguments than what we know today. And you will see some applications of this in Tom's lecture. It also implies optimal hardness approximation results for several problems of interest. And again, you will see there is a first connection you will see in Tom's lecture, but there is like a whole body of work exploring that connection further. And some of those results are kind of missing because seems like we're missing an answer to this, a positive answer to this conjecture. Now, this sliding thing here refers to the fact that you get to choose the soundness error that can be anywhere between something close to 1 to something pretty small, 1 over poly. And for any setting of those parameters, there is a PCP that is going to work for that. Okay. Now, there are constructions that get close to this conjecture, not quite resolve it, still, I would say, pretty open. But the goal of today is to talk about why would somebody formulate a conjecture that specifically looks like this? It feels like it's coming out of thin air. why not, for example, wouldn't we be able to expect an exponentially small soundness error with an exponentially large alphabet? Like that is not something that is allowed here. It's saying that you can only expect a soundness error. There's at least one repoly for this alphabet, but it's not saying that you can, if you're willing to go for a larger yet alphabet, you can have an even smaller soundness error. And there are some deep reasons for that. We're going to see them today. Okay. Wait, so let me just go back here. Any questions about this slide? So basically, like the main point I would like you to take away today is that kind of PCPs, and as we will see also IOPs, on their own with like constant soundness, with constant query complexity, will at best give you one over poly soundness error, period, regardless of what's the size of the alphabet. Okay, this is like an important sort of feature or like limitation that unfortunately they must satisfy. No more questions? If not, then let's continue. Or actually, before continuing, I would say, yeah, I mean, this is a great sort of open question. If you like to work on hard open questions, this is one. One can probably bite off smaller chunks of progress. There's about 3-4 papers that are kind of getting closer and closer, but kind of none of them really get close enough. And definitely a very nice and well-motivated question in PCP. All right, so let's talk about where this conjecture could come from. Why do we have such limit? Why is that like the right boundary for parameters to make sense? So here I've copied it again. So now let's build some very basic intuition. Okay, suppose you give me some PCP for some language with some parameters. Now we're going to make some observations. Let's say, for instance, that for this PCP, there is some instance not in the language and some randomness and some PCP where the verifier gets fooled. Okay? So it says the wrong thing, which is reasonable, right? I mean, this, you might expect it to happen. That's why we have sort of probabilistic decisions. It means that sometimes, at some point, there is some malicious proof that it says the wrong thing. Okay. Then it's pretty easy to argue that the soundness error must be at least 2 to the minus r, where r is the randomness of the verifier. Why? Because that's the granularity of the verifier's probability space, right? We're saying that the verifier is reasoning in little chunks of probability of 2 to the minus r each, right? The soundness error must work for every instance, right? And any malicious proof. And so if somewhere, for some randomness, something goes wrong, the soundness error cannot be smaller than the granularity given by the randomness. Okay, that's like pretty clear. I'm not going to argue it formally. I think that's like reasonably intuitive. Another observation says, if there is some instance for which, for all randomness, you can fool me somehow, okay, then the soundness error must also be at least basically the kind of the fraction of views. At least this is basically saying there is one local view that will make me accept when I shouldn't, right? So if I make q queries of sigma in q queries and I get answer from sigma, it means that there's a total of sigma to the q possible local views I could get from the proof, right? And if we're saying that for there is some instance such that regardless of the randomness, there is some proof that will make me accept, then in particular, a random local view will be satisfied with at least this probability. And so the soundness error must be at least this much. Okay. And if you look at like the constructions of PCPs we've had, if you give me the randomness and it's always possible to give me the randomness for me to concoct a local view that makes the verifier accept. Okay, this is like generally something that can be done for natural PCPs. So, and you could say, well, but these are conditions that you're assuming. We had a general PCP, right? Like, of course, if I start restricting the PCP in some way, maybe it will have some limitations, right? Why is it okay to assume these limitations? Or at least, why is it safe to assume these kind of reasonably okay PCP conditions? Well, if not, then something weird happens, okay? So if it's if it's never the case that for an instance not in the language, there is some randomness that makes the verifier say the wrong, rather, to put it differently, if for every instance not in the language, there is always some randomness that regardless of the proof makes the verifier say the wrong thing, makes the verifier reject, which is what it should do, then the language is not too hard to begin with, okay? And now we have here these parameters kind of participating in a very interesting way, right? Because if they're too small, in particular, the alphabet is too small and the query is too small, then the language cannot be too hard. So we can use perfect completeness and say, so let's just prove this lemma. It's like a pretty simple lemma. But with perfect completeness, we know that there's always a way to make the verifier accept for any randomness when X is an L. So therefore, the decider will work as follows. For the given randomness, or rather, so I didn't talk about the decider. So we want to prove that the language is decidable in this much time. So let's construct such a decider. The decider will work as follows. It will iterate over all possible random strings. That's why we have this exponential to the R, right? And then it will inspect all local views. And if all local views reject, then it's going to reject, okay? Otherwise, it will output 1, all right? Why? Because under this condition, this is the right thing to do, all right? Like it is a safe thing to reject when this is the case, and it is safe to output 1 when otherwise, because of this condition, right? All right, let me just pause for a second. And I'll come back to this proof in a moment if there are questions. The point is that, whatever this technical thing is, it's telling us that unless we have this weird condition, in which case these parameters, we have this kind of inclusion that means the language is not too hard, we deduce that the soundness error must be at least this much, okay? So that this regime of epsilon being at least 1 over poly is the right thing to do when the randomness is small and the query complexity is small, okay? However, this like sort of explanation doesn't quite help us if we have a large random string and a large alphabet, okay? Or we even have imperfect completeness, all right? So just take a step back. What we're trying to do here is to basically try to use elementary reasons to explain this, and we did not succeed in doing that. We basically got some limitations, but they require us to assume, in order to derive something like the slightly scale conjecture, we had to assume that the randomness is not too much, the alphabet size is not too large, or we have perfect completeness, okay? We would like to somehow derive limitations that are much more robust, okay? And the reason why, again, we went through these is because these are kind of the first few steps you would take to try to explain to yourself this one, but you will find that they're not quite deep enough to explain fully where this comes from. All right, we just pause for a moment and see if there are questions. Let me put it another way. If we want to try to lower bound the soundness error of a general PCP, we want to, at high level, we want to say, well, for these parameters of sigma, L, Q, and R, you cannot have better epsilon than some expression of these other parameters, right? Because intuitively, the bigger the alphabet, the longer the proof length, the more queries, the more randomness, this should all help you. having a good soundness error, right? The question is, what specific expressions about them are going to lower bound your soundness error, right? Natural guesses that come up are things of this sort, that, yeah, like somehow the granularity should matter, like local views, at least one of them should be acceptable generally, so a random one will generally work. So you expect some sort of dependence of this sort. But to justify to yourself that indeed this is the case, you have to kind of assume certain properties, and you have to convince yourself that if those properties don't hold, then the language is not too hard to decide. But even then, yeah.
Alexander, can you please say again? So the conjecture is this bound is achievable, or the conjecture is that you cannot do better? So the conjecture is that you can have this polynomial decay in.
Yeah, so thank you for the question. In some sense, it's both, right? The conjecture says it is achievable, but it is formulated in this parameter regime because people believe that something better is not achievable. So it's not like the conjecture says, please prove that it is achievable and that it is not achievable beyond that. It is formulated as such because there is strong evidence that anything beyond it will not be achievable. And in fact, we'll see evidence for that today. Okay.
Okay, but there is kind of no proof of lower bound, which is something like not ridiculous.
Well, we'll see strong evidence that
that
you cannot achieve better than that. But part of the reason why I went through this is that kind of why it's not achievable beyond this is not a fully elementary reason. There is like some deeper reasons, and a superficial reason typically goes something like this. This is usually the way that people communicate first level intuition. But this kind of basic observations actually leave out the possibility that you could do better if you use, I don't know, log squared randomness, for instance, or if you use like an alphabet that is slightly bigger, or even if you allow yourself imperfect completeness, which is potentially fine, right? Maybe if you're so interested in small soundness error, why not give up on a little bit of completeness? Maybe that's not a bad thing to do, right? And kind of this slide maybe came off as a little bit technical and not super kind of intuitive. It's not. But my point is that the elementary reasons won't get you there. That's like mainly the takeaway, right? And now we have to do something a little bit more kind of forceful, and we'll tie back. It's in a very interesting way PCPs in the high soundness regime to laconic interactive proofs. Somehow the reason why we cannot have good soundness PCPs hinges on the reason why we cannot have interactive proofs with small communication from the prover to the verifier. And this is not at all clear a priori that that's the connection, okay? Especially with more than one query, right? With one query, it's clear what to do. Like with multiple queries, it's not clear, okay? And so that's the interesting thing about, you know, imposing these limitations. Any further questions before we do that? Like the specifics here don't really matter too much. I guess you can go over them offline. We're about anyways to switch gears and prove the real limitations. But any questions about what we're about to do or this slide? Okay. So the amount of information that is read by PCP verifier is Q log sigma bits, right? That's what it does. In particular, we should be thinking that we want to impose limitations in a regime where Q log sigma is much less than n. Otherwise, you know, if you can encode an entire satisfying assignment in Q log sigma bits, then of course you can have, for example, soundness error 0, right? Because you just read the entire assignment. So we should think about the Q log sigma is, say, much smaller than n, say Q brute n or something like that. In this regime, the soundness error we're going to prove must be 2 to the minus Q log sigma, all right? Why? Because we're going to prove this theorem. It's a pretty nice theorem. So assume the randomized exponential time hypothesis, namely that 3-sat is not decidable by probabilistic polynomial time algorithms that run in time 2 to the little of n, okay? If that is the case, then we can prove that 3SAT does not have PCPs, where the amount of the information that you read is non-trivial. So this is a necessary condition. And here's the interesting part. With soundness error, that is less than what you would expect by this. So less than Q2 to the minus Q log L. And that's very interesting because it tells us that ultimately we cannot get soundness error better than Q log L, even if we jack up the size of the alphabet. There is a point beyond which, roughly log L, we're increasing the alphabet size beyond, where log sigma is like much bigger than log L, won't help us. All right. Again, you're reading Q log sigma bits from the proof. In principle, you might think, I deserve 2 to the minus Q log sigma soundness error because I read these bits. Each bit will contribute a half times a half times a half times a half until 2 to the minus Q log sigma. That is an optimistic hope, and it is saying that is not what you should expect. At best, regardless of sigma, you should expect 2 to the minus Q log L, the end. All right. So increasing sigma will help up to when it hits log L. Okay, when log L is roughly when log sigma is roughly log L. Beyond that, the only way you can improve your soundness error is either increasing query complexity or the proof length. All right. So this is surprising and non-trivial. All right. So before I start talking about the proof, which is actually rather cute and non-technical, is it clear like how this theorem feels like it says something? We have these two conditions. One of them is a non-trivial PCP. Okay. Right? Because if Q log sigma is like order of n, then I can give you the assignment entirely, right? So of course you cannot have soundness error. So this is like a non-triviality condition. And this is saying your soundness error cannot be too good, okay? Relative to only the query complexity and the proof length, right? So for example, it tells us that you cannot have PCPs with constant query complexity, exponentially small soundness error, and exponentially large alphabet. They just don't exist. All right.
Sorry, and like in the previous hypothesis, we were assuming that our query complexity is fixed, right? So if we then apply this theorem, we are saying that like if we fix query complexities, and then we are saying that
so that's this here. If we say the polynomial must be some proof length, so some polynomial. If you say that the proof length must be some polynomial, and the query complexity is some constant, the Q0, for example, from the previous slide, then we get that epsilon must be at least one polynomial in 1 over n. So it exactly tells us the regime of the sliding scale conjecture. If you want constant query complexity and polynomial proof length, your soundness error must be 1 over poly, the end. Okay.
Okay.
So this tells us exactly that. Right. So this is what I just said. We cannot expect exponentially small error regardless of alphabet size. All right. And this is a fully parameterized statement in some sense. It tells you something interesting even when Q is super constant. Okay. So the theorem follows from a generic lemma that we're going to prove that you can think about algorithms for PCPs. And this is what we're going to prove. Give me some general PCP, like truly fully general. There is some magical expression that says if your soundness error is smaller than some small enough notion of soundness error, and it is really 2 to the minus Q log L, and then something that depends on your completeness as well, then you can decide the language in something that is exponential in several relevant parameters. The important one is roughly here, okay? Exponential in Q log L log sigma, so that if Q log sigma is sublinear, then this whole thing is going to be sublinear, and it causes contradictions to exponentially hard problems. Okay. So let's just ignore for a moment, this term over here. Doesn't really matter too much right now. The point here is that it's saying that if your soundness error is too small, according to this threshold that we wanted here, then you can decide the language in time that is exponential roughly in Q log sigma, all right? Log L here is not very important. Q log sigma. And we wanted Q log sigma for the PCP to be interesting, already to be sublinear. So this is a bad conclusion. It means that L cannot be hard, cannot be exponentially hard. All right. There's a question by Bahid, why can't we have exponentially large alphabet and encode an entire satisfying assignment in one symbol? That is exactly what this condition is for. It's saying that we cannot store Q log sigma bits into like the local view and an entire satisfying assignment, right? And similarly here, like we're saying that Q log sigma is interesting only with his sublinear, okay? So it's exactly why you have this Q log sigma appearing there and Q log sigma appearing here. It's precisely for those situations where, yeah, great, good question. This other term here is not super important. Roughly, you know, since you have log of something over 2 to the minus Q log L, it still behaves roughly like Q log L, okay? And it's like a small order term, the bigger one is here. So, yeah, so this is, so directly implies the previous theorem. And this part is, this lemma has two steps. First, we're going to go from a PCP to a laconic interactive proof. In fact, it's going to be an MA protocol, a one-round public coin protocol. And then we're going to actually come up with a direct algorithm for the laconic MA protocol to some BP algorithm, okay? And these two together will give us this lemma, okay? Each of these is a pretty simple proof, and together they directly give you this. Each of them is going to be one slide. Any questions about how this relates to that and why this is a limitation on PCPs? Just pause for like 1 minute, make sure people are following. All right, and again, taking a step back, just to remind you what we're doing, there's a sliding scale conjecture, and we are on our way, or at least we're trying to prove that there is this kind of curve of parameters that is a limitation on PCPs that explains the sliding scale conjecture. And the main point is that even though you might be reading a lot of bits from the proof, Q log sigma, as long as that Q log sigma is non-trivial, what really matters for the bits of security, let's say, is Q log L, really. And so that's the best you can hope for. Also, kind of looking ahead, I'll just mention that both for PCPs and for IOPs, achieving this lower bound remains, more generally than the sliding scale conjecture, perhaps one of the most exciting and open questions right now is just like, how do you construct things that achieve this for a general Q, okay? Okay, anyways, so now we're going to go through each of these steps, okay? Let's first go from a PCP to the laconic MA protocol. So what we prove is that if you give me a PCP that satisfies this too good of a soundness error condition, then there is an MA protocol where the soundness error did not change. The completeness took an enormous hit. It went from epsilon C to something much, much small, much, much bigger, like 1 minus 2 to the minus Q over log L.
I'm sorry,
yeah.
Can I clarify? Basically, like given the theorems that we are now proving, like, and if we assume that BPP exp languages like do exist, maybe not specifically 3SAT, but for example, right? Then basically we have this lower bound, but even not like, so then we know that this bound cannot be like 1 over super polynomial, not only like.
Yeah, exactly.
Okay.
Yeah,
right.
But specifically for 3SAT languages, right? It could be that you have some language that is decidable in some sub-exponential time or some quasi-polynomial time, and you have to then see what comes out of this particular theorem. But this is a fully parameterized one, and for 3SAT, it will tell you such things. Okay. Good question. All right, so now we're going to prove that under this hypothesis that the soundness error is too good, and this is the same expression from a previous slide, we can construct an MA proof with the same soundness error as the PCP, The completeness took an enormous hit. It went from epsilon c to 1 minus, basically 1 minus epsilon c multiplied by something very small. So it's basically very close to 1. And the prover communication is q log L log sigma. Okay, so let's say small. And like actually, if you want to be like super precise, like the real thing that you want to pay for here is not really q log L, it's something more related to the query entropy. Okay, so the more predictable your queries are in a very precise sense, the kind of bigger is this sort of forbidden regime. Okay. So let's prove it. It's actually pretty simple. So we have a PCP, and we construct an MA protocol as follows. So here's the prover, and the prover, what will it do? We'll construct the PCP according to the PCP prover. It will guess what the queries, the verifier will make, and it will just say, "Hey verifier, here is the proof. Here is the queries that I guessed for you, and here's the local view of those queries of the PCP that I computed." Okay, so it just sends like a partial PCP restricted to like a local view that the prover thinks is where the verifier is going to look. The verifier receives this MA proof, right? Then a certificate. It's a short certificate, of course, and it, regardless of what the prover did, it will sample its own randomness and run the PCP verifier and answer every query according to the local view. And if any of them are outside the local view provided by the prover, then it just rejects. Now, it's pretty easy to see that if the original PCP, had a certain soundness error, completeness error, which means that the honest proof convinces the honest verifier with probability at least 1 minus epsilon c, then with probabilities that at least L choose Q inverse, which is roughly 2 to the minus Q log L, the prover guesses the right set, right? Because it's guessing Q locations out of L of them, right? And so, the probability that the verifier accepts is at least this quantity times the probability that the prover guessed the correct one, which means that the soundness error is the one that I wrote up here, 1 minus that. The soundness doesn't change, right? Because somehow kind of the verifier is still running as before, and it's as if it's running with a normal PCP, it just except that the parts of the PCP are missing or invalid, right? So the soundness error is definitely not going to go up, right? So to say it more formally, if X is not an L, and suppose there is some PCP, some MA proof that makes the MA verifier accept, then we can always take that thing, extend it arbitrarily into a long PCP, and that long PCP will make the PCP verifier accept with more than that probability, which is a contradiction, right? So it must be that the soundness error is the same. And the prover communication is just the size of the specifying the set and the local view. So that's Q log L plus Q log sigma. Okay. And that's it. Okay. So basically, what we're using here is the fact that we can take a hit in 2 to the minus Q log L because of guessing. Okay. We can go from an PCP to an MA proof by taking a hit in the soundness, in the completeness error that is proportional to the guessing probability of the query set. Okay, and guessing the query set has nothing to do with alphabet size. It has only to do with the number of queries and the proof length. All right. Now, why did we say that the soundness error needs to be small enough? Because for this to be an MA proof that is valid, let's say, you need the soundness error to be less than 1 minus the completeness error. Otherwise, this is not an MA proof, right? That's why it's important that the soundness error is small enough than this quantity over here, okay? All right. So if this one is too small, Q log L is too large, it means that it will kind of go below epsilon S, right? Great. And this is step 1. It's a pretty simple Q proof. Any questions about it? again, we have used this explicitly, okay? We have used this condition already.
Sorry, and MA is, it refers to the fact that coins are public.
So MA means it is like NP, but the verifier is allowed to choose randomness, okay? So it's like a one message proof that so it's like a one message protocol followed by a probabilistic choice, a probabilistic kind of a certification, okay? Okay. And indeed, it is what it's here, right? The prover sends some proof, an NP certificate. Just the verifier to check it uses randomness. Okay, so MA is like probabilistic NP. In particular, that's a very special type of interactive proof. So in this second step, in principle, what we could do is just go back to the general purpose limitations on interactive proofs. The main reason why we're not doing that is because we would have to reprove them in the fine-grained world with parameterized completeness errors and soundness errors, which can be done. Instead, what we'll do here is just use the fact that we have a very specific, simple interactive proof. It's an MA protocol. I might as well just directly work with it. Okay, this is just a much more apparent direct proof. So the second part says that if we have some MA protocol with some completeness error and some soundness error and some prover communication, then we can decide it in time that is exponential in the prover communication and polynomial in 1 over this gap. This is basically the gap between the completeness and soundness, right? Because the completeness is 1 minus epsilon c and the soundness error is epsilon s. And the difference between them is the gap between them, all right? So, and the proof, again, is like the direct thing that you would do is you are just going to estimate the acceptance probability for every possible MA proof, okay? So here's the algorithm. For every possible MA proof, sample some representative randomnesses and compute the number of accepting ones. And if the fraction is, let's say, above half the gap between completeness and soundness, output 1, otherwise output 0, okay? And by a concentration bound that I'm going to write down here, things work out, okay? But this is like, it's exactly what you would do, right? Like you have an MA proof with a certain completeness and soundness error, communication complexity. You just try all MA proofs and you see, you know, for each MA proof, whether you can find one that is closer to epsilon c or epsilon s, right? So you can define indicator variables to be the indicator whether MA accepts on that proof and that randomness. And so across different randomnesses, these are just IID samples from a Bernoulli distribution whose bias is the probability that the verifier accepts. And you know, with some additive Chernoff bound, the probability that the estimate is a kind of farther away from the probability than more than some alpha is this one. And we do know that the correct probability is at least 1 minus epsilon c if x is in L, and at most epsilon s if x is not in L, which means that to distinguish these two cases, we just need the additive distance to be less than half the difference between these two cases. And that's exactly where this expression comes from. Okay. So again, it's just a direct application of Chernoff bound. It's like statistical estimation. All right. And the statistical estimations are exactly the kind of things that, if you think about it, were happening in the lower bounds or the limitations or interactive proofs that we proved, right? So when we proved, we had this big tree, right? We couldn't afford looking at the big tree. We took subsamples of it, enough samples so that the estimates were good enough, right? Here, it's kind of similar. We don't have time to go over all the randomness. We don't want to. We are going to go through, of course, all the prover things because we are allowed to pay exponentially in the prover communication. So we take samples on the things that we cannot afford to go over. And then we just need to take enough samples for the estimate to be good enough. In this case, the estimate cannot just be some constant. Like in that case, it was maybe we did it to 1 over 10, the estimate, or forget, something like that. Here, because we have a general completeness error and a general soundness error, our estimate has to be measured against those, right? So we're going to take half the distance between completeness and soundness. And so it's just basically like a fine-grained version of the same argument we've done for general interactive proofs.
Sorry again, but but to generate those proofs, like MA, we don't assume that prover has bounded resources, right? So it can have, it can generate this views like by some very complex process. And so how do we know like its distribution? How can we simulate it with PPP?
Well, we don't, it doesn't matter where they come from. There's only so many. Because the MA proof has size at most PC bits, we can go over all 2 to the PC bits. And that's all of them, right? Because we only need to distinguish the case whether does there exist a proof with high probability or are all proofs with small probability.
Sorry. So you mean that we only sort of like randomize over randomness of the verifier, right?
Yes,
so,
exactly. And that's also what was happening for interactive proofs. We always had a bound on the communication transcript from prover to verifier. So those, we always considered all of them. In the limitations for interactive proofs, we were subsampling only on the verifier side of things. Okay, and what was making it complicated in that case was that we had a tree and we were subsampling up to every layer and also including the last layer. And potentially subsampling with private coins was even more complicated and we didn't see it in class, right? Here we have a particularly simple interactive proof. It just says prover sends a message, verifier samples randomness and decides, right? So the decision, kind of the thing we need to do is a pretty simple estimate. We want to distinguish whether there exists a proof with high convincing probability or maybe all proofs have small convincing probability, which means that it suffices to estimate to a high enough confidence every single possible proof so that we can just tell apart these 2 cases. All right, so it's statistical estimation for every single proof. Great. And when you put these 2 steps together, if you see here, we have 2 to the PC. But what was PC from step 1? Well, let's see. It was this expression, right? This is the expression that was already appearing in exponent. And then we have this up here. Oopsie. In step 2, another dependence that we have is polynomial in 1 over the gap of completeness and soundness. But what is the gap of completeness and soundness? Well, it depends on step 1. It is this thing minus that, right? And indeed, if we go back to the lemma that we wanted to prove, that's exactly what we see here. Well, you know, with a log in front because it's a polynomial downstairs. It is this one minus that, right? So yeah, we've proved it. That's from PCP to laconic, and from laconic MA to a BP algorithm. And this is how you construct, let's say, fast algorithms to decide PCP languages when the soundness is too good. And now I go back and sort of the point here was that there are some non-trivial reasons for why PCPs cannot have too good soundness, okay? And they have to do with the fact that if they have too good soundness, you can somehow shoehorn a PCP into a laconic interactive proof. And we already seen that laconic interactive proofs have limitations, okay? All right, so we're past all the heavy part of this lecture. We have some light part towards the end, but before we get to the light part, any questions about this this part? I really like this limitation. It's a very there's also a question of whether one can push much further beyond it and sort of quantify maybe some of the constants or whether certain parameters can be like improved. Feels like the right path, but maybe one can further optimize it.
So I have a question. So when we take this strong hit on completeness, why should it be? Couldn't it then become the case that the gap between soundness and completeness becomes not noticeable anymore? I think you explained this, but I didn't.
Yeah. So
understand.
This is the condition that ensures that the gap between completeness and soundness is positive. Okay. Once it is positive, it is something, right? And that something will affect this term, right? So if, for example, this difference is super tiny, then you won't get a contradiction, right? But that's, where this is a fully parameterized statement. That's why, up here, I made the gap pretty big, right? When you say little o of that, it means that these things and that thing will be pretty separated. At least, let's say, at least a constant, right? But basically, like, this is fully parameterized as long as there is a positive gap of any size. Whatever that size is already accounted for in this difference, okay? Your question. Great. Okay. So now comes the question of, okay, that was the limitations for PCPs. Could it be that IOPs help us overcome some of these limitations, right? Maybe we cannot construct PCPs with excellent soundness, but we can for IOPs. After all, we've seen examples where, for instance, the proof length for PCPs was kind of difficult to bring down, but for more rounds of interaction with IOPs, we saw how a natural approach of taking more rounds of interaction and leveraging things like Fry helped us reduce proof length to linear, which is still remains a big open question whether it's possible or not for PCPs. So this brings to the topic of limitations for high soundness IOPs. Okay. And the answer, in some sense, the first order, surprisingly, is no. Okay. There are some things that can help, but it's not like they're like a very different beast. The algorithm is that one can take the approach that we took so far of PCP to laconic something, and then from laconic something to algorithms, and basically redo it for IOPs with some extra losses, but these losses are not really big. Okay. So let's kind of talk about this. We're not going to prove anything. We're just going to state what is known. So more detail, similar to PCP, the amount of information read by the verifier is Q log sigma. And so when Q log sigma is sublinear, that's when it is interesting. If it weren't sublinear, then of course we're going to have soundness error 0 because you can always stash a verifier in those Q log sigma bits. And basically we can prove that the error is roughly still, must be at least 2 to the minus Q log L, regardless of sigma. And here's a technical lemma that basically says we have the same thing with the same, really the same expression here. The one difference is that if you have a certain number of rounds, this other term will depend slightly on it. And I haven't really updated the slides, but there is a way to mostly make this go away. With the colleagues, we haven't really worked out exactly how much it can go away, but let's say morally it can be mostly gone away. So if you just go back to the slide and repeat whatever I did, you will get this dependence here. But there are like more sophisticated ways to basically make it go away. Okay, whatever. Anyways, the bigger term is anyways this one, and I've highlighted in blue, or at least this light blue, the only differences from previous lemma. We're talking about IOP rather than PCP. There is round complexity, and round complexity shows up here. If you turn this to PCP and this to 1, that is the theorem for PCPs. So it's like very analogous, okay? And actually, curiously, historically, this was first discovered, and then in hindsight, the other one for PCPs was understood. It's kind of curious that sort of the general result for PCPs came up only when people started asking questions about IOPs. I guess maybe a strange historical anachronism. And the proof has 2 steps. Like before, we're going to go from a public coin IOP to laconic public coin IP protocol, and from a laconic public coin IP protocol to BPV algorithm. And the way you do this first step is actually quite similar to the previous first step. You're going to basically guess the answers and send them. The main difference is you have to guess for different rounds separately. And so you preserve kind of the round complexity of the IOP. And that's why you're going to have an IP protocol rather than an MA proof. And that's why for the second part, you cannot directly leverage what we saw in the Monday lecture, but you have to reprove those results for general completeness error and soundness error. You're going to make those parameter dependencies bubble up to the final dependencies on the BP algorithm running time. But they will depend in some natural way, and they will kind of come out similarly, okay? Maybe with some slightly different polynomial factors, which anyways won't matter in the exponent. And yeah, so this is roughly the the takeaway that as of today, we know that IOPs can help us a lot with proof length. We do not know yet how they can help us a lot with a soundness error. And we have evidence that maybe they don't help too much, okay? Now in practice, of course, proof length is very, very, very useful, okay? And so even if up to polynomial factors, PCPs and IOPs, so up to polynomial factors in the proof length, PCPs and IOPs might be quite similar asymptotically. The fact that you can achieve good parameters within your proof length in IOPs is incredibly important, okay? We would not have any practical application if we had anything that had length, quasi-linear. Like already T log cubed T is like a deal breaker in practice, okay? These things like start blowing up very, very fast, okay? Any questions about IOPs? We're not going to prove this, but the proof is like some more complicated version of a PCP version. Yeah, there's a question.
Is it not slightly counterintuitive that you can totally get rid of the dependency on the number of rounds when you express the, I mean, so it's not in this slide, but what you were saying that in your recent work, you're somewhat managing to get rid of the dependency. It seems very...
Okay, so here's some intuition, okay? So the first thing you might think, look, why do we have, like, why should K be large? Maybe Q anyways is comparable to K because maybe you're reading some query from most rounds, right? Some location from most rounds. I mean, really, we should write here Q instead, okay? And intuitively, that's roughly what happens, okay? That you cannot have so many rounds and so few queries and also very good soundness error, okay? So you can, there are natural constructions where you have more rounds than you have queries and you're kind of picking from rounds, but it has sharp limitations in soundness. So you expect like K to be roughly Q, okay? And so when you put Q here, then it's like you're looking at Q squared log sigma rather than Q log sigma because this Q goes in front, right? And yeah, Q squared log L, sorry, they're in Q log L, right? Because this Q log L goes in front roughly, and you will have Q times Q log L, right? And log K, even if it had been still log K, is under log, and so it doesn't really matter, okay? So the intuition is that kind of it doesn't really make sense, or one can prove that it's not very helpful to have Q much less than K in this high soundness regime. Okay, that's roughly intuition. But yeah, like it requires some observations beyond what we've seen so far. And what you've seen so far, there is no evidence that K can be gotten rid of. Okay, great question. Further questions? Okay, so and so taking a step back, so this IOP front of constructions is quite open, both in terms of what are the limits of positive constructions and what are the limits of kind of what is not possible. This is just one such thing, but more generally, like we don't have strong separations between PCPs and IOPs. It would be beautiful to have some statement that says, I don't know, if P is not equal to NP, or I don't know, if polynomial hierarchy doesn't collapse, or if exponential time hypothesis holds, then here's a regime of parameters that is provably achievable by an IOP and demonstrably not achievable by a PCP. Okay, so we don't have strong separations. For all we know, everything achievable by an IOP is also achievable by a PCP up to polynomial factors in proof length. Okay, so it's a great question. I think it's definitely worthy of study. And more generally, this front of high soundness IOPs and PCP constructions is still not something that we understand very well. We have great tools for reducing proof length. You've seen, for example, yesterday, interactive proof composition, right? So that when you compose proof systems, you don't have to consider all possible choices of random string. That's a paradigm. But there are paradigms for constructing high soundness PCPs that don't seem to gel well with interaction. It's not clear how you would do better if you had more rounds. And so that's a question remains open, and it would be surprising if there aren't things to be said in that direction. But I think it's for those of you who are interested to kind of continue thinking about building off in this background and try to think in some of these directions, I think those are definitely kind of fresh, open questions that have kind of come up basically just in the last few years. I think this is a good time for me to maybe stop and take further questions. So let me stop the recording.